Hello, everyone, and welcome to today's webinar titled Processing NOAA Weather Data in R. This webinar is sponsored by EPA's Water Quality Modeling Workgroup, and I am Jason Gilday with US EPA. I'll be moderating today's webinar. Thank you all for joining us today. First, I'm going to briefly summarize some of the features of today's webinar. We hope that you'll have lots of questions. Please submit your questions in the questions box on your control panel. There will be one break for questions near the end of the presentation. If you have any problems viewing the broadcast, just let us know in the chat box and we will post an answer in that same box. This webinar will be archived for later viewing on EPA's Water Quality Modeling training page. Also, at the end of today's webinar, you will be sent an email with a certificate of attendance. The materials in this webinar have been reviewed by US EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of EPA. And mention of commercial enterprises, products, or publications does not mean that US EPA endorses them. So the purpose of today's webinar series is to help water quality professionals better understand water quality modeling and how models can be used to solve problems facing water quality regulators. Today's webinar is the 34th in our water quality modeling series, and all of our past webinars have been recorded, archived, and posted to EPA's YouTube channel. Links to the archived files are available on our modeling workgroup website. Further, in a few weeks, a copy of today's webinar archive will be posted to the same website. We encourage you to listen to any of the previous webinars or share access to these files with your coworkers. The target audience for this series is a water quality professional who may use, want to use, or review models as part of their job, but who does not necessarily have a modeling background. As such, we are assuming that the audience has a basic understanding of water quality science and concepts, but has limited direct modeling experience. So I think that's it for the intros. With that, I'm pleased to next introduce our speaker for today. Our speaker today is Dr. Brian Picard, and Brian is a landscape ecologist and geospatial data scientist with 11 years experience conducting geospatial research. Focusing on modeling, land cover and land use change, climate, nutrient fluxes, and habitat condition. Specific emphases of Brian's include urban growth modeling, designing ecosystem service tools and models, creating novel standard for assessing geospatial accuracy assessments, watershed analysis, spatiotemporal model coupling, and data dashboard development. Prior to working for Tetra, Brian was awarded the Kravis Postdoctoral Research Fellowship with the Environmental Defense Fund and has previous experience working for several federal and private geospatial consulting firms. And with that, I'd like to hand things over to Brian to kick off today's webinar. Thanks, Brian.
Thank you, Jason, and to all who have joined. Thank you for hopping on today. I certainly appreciate it. Let me make sure these slides start moving a little cleaner there. So just some background. This is the 34th webinar, as Jason had mentioned, but actually this is the fourth in kind of a mini webinar series that we've also been focusing on. So if you've been following along for the last few webinars, we have basically been spending a lot of time in R, and we've looked at processing water quality portal data. We've looked at USGS streamflow data and NOAA weather data. Dr. Kateri Salk led those three webinars. She's my colleague and collaborator here at Tetra Tech, and she did a really nice job of kind of getting folks experienced with and used to working within R. We're now taking a hard left turn. We're going to now jump out of R and into Python and look at parallel kind of ways that we can do things in ArcGIS and in Python. So I always like to when we do these types of kind of broad sweeping collections of webinars, it's always really nice to kind of throw it out there that we're covering 2 programming languages, numerous types of analyses and different programs and processes. So if you don't, if things slip by, it's okay. And Italian in 5 1-hour webinars or hour-and-a-half webinars. So I would encourage you to think of this as a good way to gain more familiarity. If you've been using Python or R before, to maybe pick up some new tips and tricks. And if you haven't used these things very much or if at all, this is potentially a great way to kind of get your feet wet and see how you can kind of sequentially move through from say using ArcMap or ArcPro and get into a Python environment in a more repeated analysis type framework. So I would be remiss if I didn't say today we're going to focus on kind of what I would call the building blocks to the next workshop, which is delineating watersheds in both ArcGIS and in Python. I know that's been a topic of interest, and we're excited to get to that. Today is really focused on establishing some good groundwork of how we get things ready for that. So we're going to process gridded weather data, and we're going to use kind of a simple example and show how we would do it in ArcGIS and how we would do it in using ArcPy and some Python calls and model builder. And then we're going to transition into a full Python environment and talk about how we would do that in Python, in a completely Python environment, excuse me. With that, really will set the stage so that we can then have the building blocks we need to talk about a much more complex set of analyses, which would be the watershed delineation piece. So stay tuned for that. That'll hopefully be in basically a month from right now. So what are the goals for today? We have 3 overarching goals, which is to incorporate reproducible and efficient workflows into our data workflows and processing of geospatial data. Hopefully by the end of today, you will know how to acquire, process, and start to explore common types of data used in geospatial analyses. And in particular, I think a lot of people have probably at least had a touch point with ArcMap and ArcGIS. Hopefully that will also now be the case at the end of this, that you can say for Python as well. And then you will walk away as well with scripts that you can use for future use for both downloading and processing data, gridded data, and as well as hopefully some good help text that goes with each of those to help you kind of modify them for your own individual needs. So hopefully when you registered, you got a Anaconda installation guide, because we are going to use Anaconda today, and we'll talk about that in a brief second. Kateri or Jason, if you wouldn't mind throwing in the link in the chat down below, that would be very helpful. If you did not get Anaconda set up and Jupyter set up beforehand, it does take anywhere, depending on your computer, from 5 to 10 minutes. We're going to kind of do some overview slides to start, so you can probably download it, get it installed. It's a very straightforward installation, so check that out. And if not, if you're unable to get Anaconda installed, I know there was 1 or 2 folks who were unable to. That's okay. I would suggest that you can watch along. All of the code is provided with nice kind of helpful sequential steps, and so you can really kind of work this through at your own pace, as well as we record the webinars, and you can review the webinar at a later date as well. So as I said, we're going to talk about climate data today, but really what we're using climate data as our example, and we're going to use PRISM climate data from Oregon State and the Northwest Alliance for Computational Science and Engineering. But really the methods that we're going to go through today about pulling data from an FTP, unpacking it, displaying it, that can all be done for really any spatial data. It doesn't have to be gridded. It could be vector. It could be tabular. You know, these Python methods are pretty robust to that. So today we're going to talk about PRISM, and we're going to mostly focus on kind of standard climate data that we're used to. So precip, temperature, and again, it's mostly about the methodologies, the code, rather than the specific data itself today. Now, on the next webinar, it will be much more specific to watershed delineation to DEM, resolution, those kind of things. So we'll get into that. As I said, so if you aren't familiar with PRISM climate data, most folks are. It's a rather ubiquitous product. It's used all over the ecological sciences. This group basically takes a massive amount of monitoring data, station data. They apply downscaling methodologies and various control measures, and they provide a whole range of spatial climate data sets. So they provide short and long-term climate patterns and historical climate data. So you can look at monthly, sometimes daily, yearly, 30-year normal data from 1985 to the present, and it covers things like temperature, min, mean, max, precip, vapor pressure, dew point. You can see solar radiation, elevation, etc. And so a lot of this data can be fed into much more robust modeling efforts, various analyses, etc. So if you haven't had a touch point with PRISM's data before, I highly recommend checking it out. We'll get to see it today, and hopefully that'll be a good precursor as well. So since we are switching from R to Python and ArcGIS today, I just wanted to take a quick second to jump into quickly what defines a spatial data set versus the tabular data that we have worked with in some of the previous workshops. So really it's location. We are now assigning a process or a representation in space. So there's now coordinates, there's now a location and data on that location in space, as well as whatever process or representation that we're interested in. Excuse me, and that also holds true for time as well. So it's location, 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 and through time. The other key defining point of a spatial data set is that there's heterogeneity. So there's variation across both the space and through time. And then we can get into a little bit more of the nuance of kind of key aspects of spatial data. So spatial resolution is one that always comes up and really can have pretty profound impacts on your analysis, on your modeling efforts, on your computational processing and efficiency times. So it's really something to always kind of keep in mind in the back of your head. It very much can determine what is left out of the model. If you have too big of a spatial resolution, then you might lose information or lose data or granularity. It determines, as I said, the cost of collecting that data, of running that model. I think now in particular, we're seeing so much data coming into us so fast and at such high resolutions that sometimes that doesn't feel like a problem, but it can be. And with that much more data and higher resolutions, it really means that things can take longer to run, and computationally there's a lot more to do. And your resolution, more than anything else, contributes to your accuracy and what you are using that data for. That's always something that we want to keep in mind. These are very much this corollary in the temporal resolution aspect as well. So whether you're looking at things over a year or a day, you're going to have different results, and it's these same things are very important to remember as we think about our spatiotemporal resolutions. So we're going to talk today about, or we're going to talk and use today, ArcGIS and ArcMap. For some of the folks out there who are probably aware, we're all going to lose ArcMap if you are an ArcMap user. And Esri is going to make us go to Pro very soon. I use both. I used ArcMap today because I think more people have touch points with ArcMap than maybe ArcPro, but really everything that we're doing today is transferable to Pro. So I don't think there should be any worries there. For those of you who are new to some of the different platforms that are used, there's really kind of two camps. There's Esri and everyone else, you could say. Esri dominates the market. They are pervasive throughout academia, government, NGO, etc. most people at the EPA, for example, are going to be virtually forced to use or close to being forced to use Esri-related products. In some of the other sectors, academia and geo, you may be more inclined to use some of the other open source options that exist. So QGIS is very popular. GRASS-GIS, the GRASS GIS hub for North America, is actually just down the street from Research Triangle Park and at North Carolina State. There's various open source packages, which we'll actually talk about and use today as well. And then you can do geospatial modeling in R. It takes a savvy R user, but it can be done. And there are times when it actually can be advantageous. So that is something to think of as well. So if you've been following along in the, this series of webinars, we have been, Kateri and I have been putting all of the data and information for each of these webinars kind of nice and neat on a single GitHub repository. So the first thing that we're going to do today that I would encourage is for everyone to go to github.com/KateriSalk/EPA water quality modeling _webinars. Go to this page. I will do it as well so that we are all on the same page, which you can see right here. Open it up. And then if we go to this green code button, go ahead and click on this download zip, and we'll let it download. It'll take just a second. I'll put that website up for just one more second, and then we'll put it in the chat as well so that folks can grab it. That has all of the data, the code for each of the sessions. It has the data and the code that we're going to use today. And we can, we'll jump into that in just one second. Okay, so I did talk briefly at the beginning about using Anaconda. Anaconda is a data science platform. So what does that actually mean? Anaconda is an open source distribution, basically, where you can essentially have a single overview program that allows for you to access everything from various Python editing platforms, R Studio is in there. You can run much more data intensive programs for machine learning. If any of you use Keras or Torch, for example, those can be accessed through Anaconda. It's very useful for large scale data processing and for predictive analytics. What's nice about it is that if you don't want to work from the command line to get into coding, this is a really nice place to start. Can be a little bit of a bear to get installed. I know some people had some trouble, but once it's in there, it's quite nice. It makes loading packages really easy. It's really, I would say, the closest thing to kind of the ease and efficiency with which, if you've used R and RStudio, this is kind of the corollary to it, even though it includes RStudio. So we're going to use Anaconda for part of this kind of hands-on part of today, and we'll walk through kind of getting things set up and working from there. When you open it, you'll see kind of this, we'll open up the navigator. This is the graphical user interface. This is one easy way to start working with it. And we can, we'll go into this in one sec. But as I said, you can see there's various text editors, Spider, PyCharm for folks who've maybe had touch points with those, Jupyter Notebooks, which we're going to use today because it's a nice kind of tutorial way to work through code, RStudio. And then you can load a whole range of other applications. What's nice about this too is that for each of your projects, you can create an environment, which we're going to do today. And then as you start to change some of the backend parameters of which packages are loaded, for example, that's contained within that specific project environment. That's very helpful as you start to share code with other folks, because you can not only share your code, but you can share your environment file, and then someone else can work in the exact same sandbox as you with all of the same various packages turned on or turned off. And it just makes it nice and clean and easy. Okay, so a little bit of the background. We're going to jump into the kind of the more hands-on portion of this today. So the question here, or the question that we're going to walk through in 3 different ways is, how do we download climate data? How do we display it? How do we process it into our geospatial modeling and workflows? So if we think about that, there's a couple ways we could do it. There's really, you could almost say 4 to many, but today we're going to focus on, can we use one of the Esri products, to really say ArcMap, not ArcGIS, or Pro? So we can do it in just straight ArcMap, and we will quickly walk through that. You'll see that we could do 1 round of it, of processing a single geotiff in a matter of minutes. But what happens when you need to process 2,000 of those and do that workflow 2,000 times? Well, that's maybe not the most efficient way. We'll look at very quickly how we do that in Model Builder. When we take the point of looking at it in Model Builder, so that we can then export that, and we can give folks who maybe haven't moved out of the Model Builder ArcMap world how to quickly get some helpful starting points for exporting your model to a Python script, then looking at how we might change that in a very kind of simple way. Then we're going to ratchet up the kind of complexity. We're going to jump into a Jupyter Notebook, which is a purely Python-based environment, and we're going to then implement basically that same workflow using open source GIS packages, and provide something that's far more repeatable for use. So as I said, these are really the kind of the building blocks. And then on the next workshop, we'll ratchet up the complexity, the difficulty, the level of coding a bit, and we'll get into kind of the watershed delineation, and then summarizing some of these data sources that we're preparing and packaging today. So the general workflow for today is very simple, but it's meant to highlight how to kind of sequentially walk through a level of complexity. So we're going to download some raw data. We're going to unzip it. We're going to display it. Also look at it from a QA perspective, just so that we can do a quick visual QA. We're going to reproject that data to match an area of interest. Today, we're going to just use a county boundary, but we can use also, we could think of that as a building block to using a watershed delineation for the following time. And then we're going to clip that data to the area of interest so that we can then use that in our various modeling. So how are we going to do that? So to start, because there's a little bit of back-end work, we're going to actually jump to the Jupyter Notebook side for just a hot second to get some stuff loading and some packages installed. And while that's happening, we're going to walk through the ArcMap Model Builder and ArcPy side of things, and then we'll circle back to the Jupyter Notebook. So for those of you who are following along today, let me move this out of the way. Step 1 is going to be, if you installed your Jupyter Notebook, you will find, if you've installed Anaconda and your Jupyter Notebook, in your start menu, you should have an Anaconda. And within that folder, you should see Anaconda Navigator. So I'm going to click on Anaconda Navigator. And this will just take a quick second to open. Try, while that's happening, to catch questions as it comes. So you'll see it's opening a little bit in the background here. Just give it 1 sec to think through. Krishna, you could test this class using QGIS. Once you're in when we get to the Jupyter side and the full Python version, it's really transferable to QGIS. So that's something to think about. Okay, so hopefully everyone followed those instructions and created an environment. So when you first open the page, this is the home page. As we talked about it, if you installed your Jupyter Notebook. You should see it somewhere along this list. You can see you can click launch, and we can launch that. Before we do that, though, there are a few packages that we're going to want to install for our specific environment today, so that we are able to do some of the geospatial and geoprocessing that we want to do. So if we go into environments in this tab right here, and you can see that I have a bunch of environments created. You likely maybe only have one or a few others. Click on the environment that you're planning on using for today, or that you created for today. So I created one called EPA Spatial Webinar. And you'll see down here that it's now loading this environment and getting everything ready for us. I promise this is the most not fun part of the process, and we'll get to the better stuff in one quick second. So we need to install 3 packages today. One of them is an overarching package that's going to install a bunch of them, so it's going to take it a second, which is why I wanted to start. So if you click on this drop-down menu, this shows you the installed packages in your environment now. We go to all, you can see there's a bunch of packages here that we could install. Exactly 9,338 are available to us right now. Yours may be slightly different, but what we're going to look for is called raster stats. So in this search bar up here, type in raster stats. This is a really, really handy package for those of you who are ArcMap and ArcPro savvy. This is zonal stats on steroids, basically. Go ahead and click on that so that we have it selected, and then down here we can actually click apply. And that's going to start to install not only this package, but a bunch of other packages. Now, while this is going on, this is going to take a minute or two. There's a fair amount to be installed on the back end here. So I'm going to let that think, and we're going to jump back now to our, bear with me, everyone. We're going to be jumping a lot today. So we're going to go back to our general workflow. So today we're going to download some PRISM data. We're going to unzip it, display it, project it, and clip it. Simple method, simple processes, but processes that happen all the time and could be batch automated. This is the PRISM website. This is the PRISM website. As we talked about, it's from Oregon State, one of my alma maters. They provide a ton of data, as we talked about before. So today, we're actually going to focus on just a really quick example of how we would do this to highlight the kind of inefficiencies of doing this wholesale. So if we click on recent years, which I have here already set up, if I wanted to download temperature precip data from January 81 through March 2022, annual or monthly values or data values, you can see you have to make a series of selections. You've got to click all these radio buttons. It can be kind of cumbersome. Just to highlight this, I'm just going to download, for a brief example, maximum temperature for 2008 for the month of August. And I'm going to click download data. And you can see we have it downloaded here. And now in a non-automated workflow, I now have to come in and I have to go to my downloads. You don't need to necessarily do this yourself. This is as much for demonstration purposes. I have to take it out of my downloads folder, as people are probably well aware, and put it into some other folder. I'm going to put it in this EPA webinar folder. And then before I can bring it into ArcMap, I have to unzip it, right? So that's the next step here. So I'll just extract the files here. Now you can see we've got, for those of you maybe less familiar with spatial data, we have a series of data here now. So we have a .bil file. This is very similar to a GeoTIFF. It's just a different way for storing things. And then we also have several other various files associated with it. One that's very important is this .prj. This is a projection file, which will be helpful and informative later on as well. So the next step will be to open ArcMap. And while that's going, I'm just going to circle back, as everyone else should. You'll probably see that at some point very soon, after clicking that install, that Anaconda is going to tell you that for this environment, it's going to that 8 packages will be modified, and it's going to install 59 packages to make raster stats work. Go ahead and hit apply, and it's going to think for a little while longer, and we're just going to let that churn in the background. Okay, so if you're used to ArcMap or ArcPro, we now are into our geospatial, our GIS environment, right? And so we've now downloaded our PRISM data. And we have a lot going on the computer, so hopefully we don't grind too much to a halt here. And we'll navigate back to our data. Go to our webinars. And you can see now that we have this gridded raster data. So we can add this data. And now we're looking at Tmax temperature, max temperature in August in degrees Celsius. So, you know, we can do things just like everyone's probably familiar with. We can change symbology. We can change symbology. We can change color ramps. I'm asking my computer to do a lot right now. Okay. There we go. Now the question is we have spatial data here. What if we wanted to create a map using a different symbology for different months, and we wanted to create these maps for every month between 1985 to 2020? Well, this is probably not the most efficient way to do it. So where people often or may end up going is to start to go to their workflow in a model builder. I'm going to turn this off for a second, just to try to save some processing speed. So for those of you who are very new to ArcGIS, Model Builder is a nice visual way to start to think about how you conduct geospatial analyses. Oh boy. Bear with me, everyone. Let's just double check. We're still installing. Good. Okay, so within our geoprocessing, we can go to Model Builder. And now we can start to do the various analyses that we talked about in our workflow. People will oftentimes get at tools from the Arc toolbox. You can also use the search feature. So the first tool that we said is, so we downloaded it, we unzipped it, now we need to project it. Okay, so we can click and drag here. Oof, sorry, everyone, this is running a little slower than I had intended. Yeah. Now, we decided we had said we wanted to project it, and then we were going to clip it so that we could have it in our analyses. So within we need our county data set. So let's back up really quick. We'll go back to our download section. If you remember, we downloaded this EPA water modeling webinars main.zip. We can extract that, and I'm going to save that real quick. See, we're almost to the coding, I promise. Go temp, and we'll save it right there. And go OK. OK. Now we can go in and we can bring in our data here. So here's our GitHub repository here. Within our data folder, you can see session 5, spatial data, we actually provided a shapefile for today. So we can add this shapefile. This is the counties of Minnesota. If we want to look at it really quick, we can see we have counties. The risk of not grinding to a complete halt. Let's go back and just make sure that our Anaconda is still working. Perfect. Okay, so now we can open up our model again. We can create this model. We're going to project a raster. Project. Okay. Oh, looks like we're moving a little faster now, maybe. Dear, oh dear. If someone could put in the chat if theirs is finished loading, that would be helpful, just so that I know. My obviously I'm doing a bit more. Okay, so we can input our raster. We're going to call an audible here in 1 second. Okay, we're going to hang on, everyone. We're going to call an audible. We are going to skip ahead. Okay, so what we're going to do here is, so for those who are used to this, we could build this in Model Builder. One thing you can do in Model Builder is to export a script, which we will do. Oh boy, everyone. There we go. Okay. So we can export a script in Model Builder. Model Builder will allow you to export that as a .py script, which we can then bring in and look at in various Python text editors, which as soon as I'm given any kind of control back to my computer, hopefully we can look at an example of. What's really nice about Model Builder's Python export script is that it's a good intermediate step between writing your own Python code. So the script will have all of the import statements, as we're going to see in 1 second here. It will have all the import statements. It will have the various file paths already encoded if you've made those links in Model Builder, etc. Oh, thank you. So we've installed raster stats. That was the big one. I apologize. We should have done that beforehand. We're going to install 2 other ones really quickly here. GeoPandas is one. Just going to click on GeoPandas. GeoPandas. We're going to install this. This should go very quick. All right, so while that's happening, let's all make sure that we have our data unpacked. So if you've extracted your your EPA, your GitHub repository, go navigate to that file. You're going to see that we have in the code folder, we have a session 5 spatial. And in this, we have a session 5 visualize spatial data.ipynb. This is a Jupyter notebook here. Which, let's see. Sorry, everyone. All right. Okay, so as yours is opening up, I'm going to go ahead and just switch right now to so that we can start to actually look at code and start walking through this while yours is loading. So if we open up our Jupyter notebook, last thing I swear will open. All right, so Jupyter Notebook is set up to reside on a HTML on a web page, but what's very nice is that it's easy to upload various files that we can look at code and helpful text documents at the same time. So I am going to go to create a new folder. And down here, we'll click on the new folder and we're going to rename it. And we'll just call this workshop. Okay. All right, and to load our Python notebook in there, we're going to click upload. We're going to navigate to our GitHub repository, wherever you saved it, in our code folder, session 5 spatial, and now we're going to upload this .ipynb. Okay. So when you click on that, what you'll see is now we've got a nice workflow where we can actually provide text and helpful information, and we can also actually run code. So I apologize if people are if their computers are running slow. Mine is obviously running very slow with Teams and Arc open. So the way that you work through these Jupyter notebooks is when you get to a line of code, you can actually run it. It has Python embedded in it, and we can start to work through there. So to acquire our spatial data, we first have to import various Python libraries. So you can see we've imported OS, which is an operating system, a URL request, etc. So we can run that just by clicking this run button. And it allows us to basically keep working our way down. So within this, so for this example, we're going to navigate to or specify a working directory. In this case, I provided the file path name here, so you can provide whichever file path from your notebook that you'd like. The easiest way is to simply click up here, copy that location or whatever location you want to do. You can tell Python that if, and this is just a simple kind of code call that says if under the operating system the path does not exist, i.e. this variable, so working directory, then I want you operating system to make this directory, and we can make this directory. So if I run this line of code, you can see that in my EPA webinars folder, I'm going to make a folder called example1 acquiring data. We'll navigate back to that real quick. And you can now see that we have example1 acquiring data right here. Really simple stuff. Now we can actually get into starting to pull our data wholesale. So PRISM actually enables you to, through an HTTP service, to download this data. There's a convoluted set of URL links that you have to specify depending on your element. So in this case, we have this HTTP services website, and then we can specify our resolution 4K or 800 in this case, our element, which can be precip, tmin, tmax, tmean, etc. And then we can specify a date. This is to do a single request. So here you can see valid examples of that. So we have PRISM, data public 4K. We want to do tmin for 2009 for April the 5th. We could do a monthly grid for tmin, etc. We can do an annual grid by just specifying 2009, or we can do a historical grid as well. So in this example, we're going to download a 4K resolution gridded data set. So we specify 4K Tmax for 2008 for the month of the 8th. You'll recall that's what we were trying to do by hand a second ago. So we can run this, and you'll see we've now downloaded that data, and we've saved it to our working directory with the name PRISM 4K Tmax 2008. In the interest of time, I'm going to skip over. We can download the normals as well. Normals are a different climate product. They provide an average over a 30-year range. They're very nice to use and can be very helpful. But I want to allow us to actually get to displaying and presenting and actually looking at some of this data. So we can run, I'm going to run this line of code, but we'll skip right over it. So if we want to do bulk downloading, we can now start to implement what's called a for loop. So for folks who are a little bit new to Python, a for loop is really just a way of telling our code for a specific set of months, for example, in this example, download all this file. So we can specify the months here. We can say, I want to know January, February, and March. And we can say for, and we can provide a new variable which calls each of these individually for month in our months variable here. Take our URL right here and add that month onto the end. So in this case, we can batch download precip 2009 for each of these various months. And then just, again, using that same code we had above, we can save it as our zip file and we can download that. I'm going to do that really quickly here. And you'll see in Jupyter that when the backend Python is working, you'll see a star here. And once it turns to a number, that'll tell you that we actually have a line that ran. So we can extend this for multiple years, adding additional for loops as well. So in this case, we can say for the years 2007 and 2008. And now you can see we've added just a second for loop. So we're saying for each year in our years file here, 2007 and 2008. And for each of those years, for each of the months within our months, download that data as well. You can have a number of nested for loops like this. It can get quite complicated, but you could imagine that if we wanted to download 10 years worth of data, now we can do it on the fly very quickly. So again, a really nice, easy way to download and batch download this data. Okay, so now that we've downloaded data, let's unpack it and let's actually start to view it and clip it and project it using Python. So we're going to skip over this exercise in the interest of time, but I encourage you to stop in here, take a look, and give this a try on your own. So to unpack our zipped data, there's a really simple set of file calls that are kind of standard for the most part that a lot of people use. So we have a package that's automatically loaded into almost all Python files called from zip file, or excuse me, that's called zip file. And so we can, this is a really nice, simple package. It knows how to unzip the data. It's quite simple. We're just going to specify our working directory and the data that we want to unzip again. And then we can load that in to this, this zip extractor. So we're going to load the zip file location, which was taken from right here. And then we're going to extract that to our working directory. Do that really quick. Okay, now if we want to unzip all the files within a directory, this is kind of the last batch downloading piece that can be quite helpful. We can do this with just a few extra lines of code, where we basically say for all of the files in our working directory, list all the files, and then for each file, if that file ends with zip, run this same code again. Really straightforward, but it'll automatically unzip all of those files in your directory. So I'm going to run that, and we can see now that now we've downloaded a bunch of PRISM data, precip, Tmax, etc., and we've now unzipped it. So we're now starting to batch process all of this data. Now comes the fun part. Run that one again. Okay, so now how do we actually start to display and analyze this data in Python? So one of the packages that you can use is called raster.io. If you've unzipped all your files, we can now use the raster.io library. So raster.io is an incredibly useful module for processing raster data. It allows for you to manipulate, transform, project, display. It's a really robust package. So here we're going to import our raster.io. And then we're going to open up one of our PRISM grids that we looked at. So here we pulled that Tmax 2008, August 2008 data. And to open it in raster, the first thing we need to do is obviously import the raster.io package. But then we're going to specify the file path again. So os.path.join, this says join my working directory path with this file name. And we can then feed that into our raster.io.open, and that's where we get this PRISM grid variable call. So now in the variable data set, we're now holding our raster in memory. So you can imagine that if it's a 1 meter data set for the entire world, that might be a lot of memory. It might have a hard time doing that. So just bear that in mind. Raster.io also allows for us to look at a bunch of useful attribute information on the fly. So here you can see we're just quickly printing off some attribute information. So we can print off the name. We do that by simply calling the dataset.name. We can print off the count, the number of bands. In this case, since we're just looking at one band, which is max temperature, we're only probably going to have one band. But if you were looking at a true color image, for example, you can verify that you have 3. If you're looking at hyperspectral data, you can verify you might have 13 or many more than that, etc. So we can look at the projection. This is going to become extremely helpful down the road. And then we can also look at things like the bounding box. So where does this data cover in terms of lat long? And then we can look at also, if we want it all, we can ask for this dataset.profile. This allows for us just to quickly look at the full profile of what's the data type, what's the no data value. This is a very kind of similar way to looking at, say, the attribute table in ArcGIS. We can run that. Oops, let's run this. And we can run that. Now you can see that we're just printing out this information that's just helpful to be aware of. We have our projection. If you've worked with ArcMap, this would look quite similar, etc. If we want to know the bounding box, so we can see our lat long coordinates for where this data actually covers, and then obviously the full profile. So we see that the data is floating point data. Our no data value is -999. We can see the number of cells we have. CRS, the coordinate reference system, is provided there, etc. So, okay, so each raster data set can have several bands, as many people are probably aware. And when we start to read this data into Python, bands are essentially arrays of numbers. So I put this here just so we can think about this as what exactly that looks like. Now remember, we have, in this case, we have a 4-kilometer grid across the US. So we have a width of 14,000 cells going east to west or west to east, and we have 621 cells traveling north and south. So we have 1405 times 621 number of cells. So we can call individual bands and look at those arrays of data. In this case, and I'll give you a little sneak peek, since we have no data values, not for everywhere that's not included in the US, we know we've got these -999 values right in here, right? And we know that because our no data values come from right here. If we were to expand this and show the entire array, you would essentially see for each of these values either a no data value or your actual attribute information, your cell value. Okay, so we've unpacked it. We've now asked to see our the first band. In this case, we only have one band, so we don't have to worry about that. But we asked to see our data, and we saw it as an array. Now let's actually start to look at it, and let's start to plot it and to streamline our plotting so that we could, in theory, make this figure for every month that we calculated on or that we have data for on the fly. So matplotlib is another really widely used kind of plotting, figure making, graphical library. And it's very powerful. People spend a lot of time focusing on using matplotlib and becoming really, really good with making these types of figures. This is a 4-line figure, so keep that in mind. We've provided a whole host of kind of starter resources, but there are tons and tons of online resources that you can just start Googling for code to make incredibly pretty and beautiful figures that are reproducible and can be created. So we import matplotlib.pyplot. This is a sub-library of matplotlib. And we use what's called, sometimes Python coders can get really lazy. So they, instead of writing matplotlib.pyplot, we can basically say import it. And every time I want to call these functions, let me just use PLT instead. So we can say import matplotlib as PLT. And there now you can see, instead of writing matplotlib.pyplot every time, I can just write PLT. It saves me one fraction of a second, I suppose. But it's quite commonly used in Python. So some basics to start plotting in this. We can look at, first we can specify a figure size. So plt.figure, and then this is pretty explanatory, fig size, and we can specify it. You can play around with this. We can make this 12 by 12 or 14 by 12 and see how that looks. You can see, obviously, it starts to change. I had it at 24. Thought that looked nice. And then we actually need to say what data are we going to display. So in this case, what I've done is we've used plt.im show, and we're calling that band that we created, right? That dataset.read. And then we can specify a color ramp. There are a number of color ramps. People make them all the time. We've in fact provided some information about various color maps that you can use here. Here we're using a color map called cool warm. If we wanted to select a different color map, we could use something like there it is. I know Kateri, if you've been following along in the webinars, Kateri used that in one of the previous ones. If we wanted to, there's a ton. You can see the lists go on and on and on. Since we're thinking about temperature here, I might try using something just as simple as reds, or maybe yellow, orange, black, just for fun, or yellow, orange, red, excuse me. I realize that sometimes with these types of maps, we have to be careful with what we specify for various policy reasons. But for today, we can put whatever we want in there. We can see those color ramps start to change. Now, I've also specified here this Vmin and Vmax. This puts a bound on the data that is displayed. So for those, for example, for those -999 data value, no data values, where we know that we don't have data out here, we could specify that as a different color. For simplicity and kind of quickness, I basically said if it's less than 0 or greater than 50, because we know that the data isn't greater than 50 degrees Celsius, then just basically add those to either end of the spectrum. And it helps for our color bar here to make it nice and neat, instead rather than having a -999 down here, etc. All little things that you can spend a long time tweaking and playing. We can add a color bar, as you see, which is nice and neat. We can add a label. We could also specify a label text size. For time, I won't get into that. We could add a grid, as you see here, if you're really concerned about lat longs. Most people are used to the US, so maybe you don't want a grid as an example. So if you want to comment it out, just similar, I believe in R, you can put a pound ampersand there, pound. And that way it'll show as green and not included in there. And lastly, we can save our figures. So in this case, we're saying, hey, matplotlib.pyplot, which we've called PLT, save this figure, save fig, and save it in the path that we are joining working directory, and we'll give it a name, temperature figure 1 as an example. You can also add this. This tends to be helpful a lot of times when you're making these figures. Bounding box is inches = tight. What this does is basically takes the upper part of any of your elements in your figure and really make sure that you're nice and truncated there. We can show if we had other raster data, for example, that we loaded up, and maybe it was only for a portion of the country, but we wanted to have it on top of this. We could simply add things like plt.im show your other layer, whatever it is, and a CMAP, etc. So you could do those various things as well. Good. I would say this is a very kind of rudimentary start to get into this. As you can see, there's a lot of resources, as I said. So matplotlib.org is a great place to start. And then you can kind of continue to work into it from there. People teach entire courses just on matplotlib. So this is kind of a good little dip your toe into it if you haven't seen it. There's a second exercise here, which I'm going to skip again because I want to continue to keep working down the clipping and some of this data extraction piece so that we're kind of ready for the following webinar. But I encourage you to try that again. It basically asks you to download an 800-meter grid for various years. unzip it, and then see if you can display them below. Lastly, I'll point out, at one point I know we had talked about, well, what if I wanted to make, say, an animation, and I wanted to have this figure, create this figure for each year, for every year from 1985 to 2022. Well, you now can make these figures with a simple for loop, right? Because we could download, you now have the information above to download all that data. You now can unzip it, wholesale unzip it, process it, and then you could, through a simple for loop, start to just simply call each of your bands and each of your data sets, and then iteratively save your files and things like that. So lots to play with, lots to work with. Again, kind of a high level, quick data visualization piece of this. Okay, so if you remember, we were trying in the in ArcMap to clip data, because realistically, what we want to be able to do is pull data, run analyses to it, clip it down to maybe our watershed of interest, and then we can start to summarize that data. So in this case, if we think about a watershed delineation, we've pulled temperature data. So if we're doing a watershed characterization and we need to know, well, what's the max temperature over these various years for our watershed or for our state or our counties, this is a critical next step, is getting this data in the same projection and ready to go for our various other analyses. So we're now going to call upon that other package that I talked about, GeoPandas. GeoPandas is an incredibly powerful package as well. I would say it's probably the most widely used open source Python geospatial package used, maybe with the exception of raster.io. GeoPandas is focused specifically on vector data. It's used to look at shape files, points, lines, polygons, etc. And what it does is it actually manipulates vector data and allows for you to seamlessly deal with it as a shapefile, but also as a data table. So in ArcMap, when we have to import our shapefile, we can look at it in ArcMap, then we have to open the attribute table. We have to call various tools or various analyses on it. You know, effectively, you have to kind of treat the table, the attribute table, in a much different way than you treat the shapefile as a whole a lot of times. This really cleans it up. It really streamlines it. So it works quite similarly to raster.io in the sense that at the end of the day, we have to tell it where is our data. So if you'll remember, we specified a data folder. That's actually not the right folder. That's an older one. So in our webinar here, in our webinar folder in data session 5, we have this Minnesota counties as just an example of data to use today. We can go in and replace that. You'll have to replace this with wherever you saved it, obviously. And then we can say, okay, this is the shapefile. It's located. Please join this data folder with my Minnesota counties.shape so that I have that full file path name. And GeoPandas, remember we called it, because Python coders are lazy, we called it GPD instead of GeoPandas. So we saved ourselves 1, 2, 3, 4, typing 6 letters each time, 6 keystrokes. So we call it GPD dot, and then it's very simple, just read file, read this shape file in. We can also, for those of you who are always interested in efficiencies, you can also start to combine some of these. Now, the more you combine in lines, the harder it is to debug and things like that. But we could also do something like that, where we say, read this file, and then we could embed this original line of, this line of code essentially in here. And so then we're not holding shapefile in memory. Minor point, but something just to kind of think about as you start to get smoother and smoother with coding. Now, once we have catchments loaded as a geodata frame, essentially, we can actually quickly look at it. So we could just plot it really fast. Hey, let's just make sure that it looks right. Data's looking okay. We pulled it in. And so the next step here is to actually clip the data. So in order to use our features, technically what we're really only concerned with here are the polygon geometries. So we're not actually worried about the attribute data in this case. We just want to know what are the geometries so that we can clip our data, our gridded data in raster.io. We can do this in a slightly more kind of low-level format. So we can use another package called Fiona, which hopefully loaded when you installed raster stats. And we can basically just say, let's just take our geometry object with Fiona in order to obtain a mask. So again, we import Fiona. We didn't get super lazy and call it F as F or something like that. And then we can say with Fiona.open, take our shapefile so we're going to take this this and basically call it vector file. So reference it as a vector file. And we're going to say that our shapes, so what are our geometries of each of these counties, is going to be basically take the geometry for each feature in our vector file, for each attribute, for each, for those that used to or maybe ArcMap, for each row in your attribute table or each row in your data frame. This is a little bit more convoluted. This is a little bit more Pythonic for those of you who are a bit newer to Python. But it's really just a cleaner way to add in. You can see we've got a with statement where we're calling something as something else, and then we're asking for data in a for loop all in one line. So this is a bit of a streamlined way to write this. You could write this in a much longer way. But for simplicity's sake, that's how it's written here. So what this does, I should be running these, sorry. Okay, got to make sure you run it. Okay, so what this does is basically shapes now becomes essentially an object that has our masks that we want to apply to our grid. So the clipping is really, as it says, it's quite easy. So all we have to do is actually call from raster.io a pre-built mask function, which is really nice, similar to ArcMap. So from raster.io.mask, this is a subset of masking tools, import mask, very original. So in this case, we'll call our grid here. So we just simply say, here's our working directory. Please join together the working directory with our .bil file. This could be a .tiff. This could be a geotiff. It could be an Esri grid. Raster.io is quite accepting of all gridded formats. And then we can then call our raster.io.open. So let's open that data file again, this PRISM grid. And then you might be wondering what this R stands for. So if any of you have worked with CSV writers or anything like that, this R stands for read. You can have it also say W for write, where you would be writing over the PRISM, this particular PRISM file here. But by specifying it as R, you're effectively locking the file and saying you cannot write over this. Just simply read it in for me. So now we have this variable data2 that we've read in, and this data2 now is our raster, right? And the next step is to basically get what would amount to a projection file in ArcMap. So in this case, what we can do is we can specify two variables using our mask function. So we have out image, which is basically what our clipped image is going to be. It's going to be that stored array, essentially, but masked to our new geometries that we took from the GeoPandas shapes from our Minnesota County shapefile. And then we can also grab this out transform. So what this does is it actually, on the fly, records the transformation to, it records the transformation that Esri typically would do on the back end. So when you load in two data sets, for example, in ArcMap or ArcPro, and they have different projections, depending on if you've turned off the warning or not, you may get a warning that says, hey, these are in different projections. And Esri will, on the fly, reproject whichever one is not associated with the first data set that's brought in, that the data frame or that the map is actually being projected in. So we can record that here, and then that way we have it in memory so that when we want to write data out, we can actually just link to that and make sure everything's in the same projection. I would say the open source world has done a much better job of making projecting things much easier. For example, no longer all of the various geographic projections and the well, really every projection in Esri has now a corresponding CRS number. It's a 4 or 5 digit number that you can easily pull from a file and just specify that number and transfer it rather than having to dig for the exact verbiage and convoluted call that Arc has. So that's a really nice piece to this, to being in Python, is projections are a lot easier. So we can grab that out, project that transformation as well. I went down a little bit of a side tangent, I apologize. So we can say mask, our data set is going to equal our PRISM grid here. Very good. Our shapes, what are we going to mask it to, is going to be the shapes. You can remember we grabbed that from our shape file. And then crop equals true. This is just a flag that you can turn on so that if crop equals false, then it will preserve the original extent of your grid. So in this case, it would be the full conus, or you can say crop it down and don't store all of that extra no data information and really just clip it right around the whatever it is we're masking. So in this case, since we don't want to store all that additional no data, we can go into crop equals true. We can then save that data. We can transfer the metadata very quickly and all of the backend projection data. And then we can update that here. I realize we're running out of time, so I'm going to skip over updating metadata. We'll try and cover that in the next webinar as well. And so then the last step is, can we save it and can we look at it really quick? So very similarly, we specify a name. Where do we want to save it to? In this case, we're going to save it again to our working directory. We're going to save it to, we're going to give it a name. I just called this Minnesota TMAX 2008.tif. And then we can use one last call here. So with raster.io, can you take the clipped image that we created? Now you'll see we've switched that flag to W because we're saying right over this file path. And then bring along all of our metadata, our projection data, etc. We're going to call all of that information together, this DEST, this destination. And then we simply say, for that, write our out image, which we created right here. And we put that right in there. And that'll write it straight to there. Lastly, if we want to look at it, we can jump into, again, rasterio.io, clip the image, use the R so we don't write over it as a variable name here, and then we can show that, and we just put in a color map really quickly here. These data look pretty coarse, obviously, because we're dealing with 4-kilometer grids. If that was a 30-meter DEM, it would look much different. So I realized we had a little bit of a derailment due to some computational lags of having a lot of things open, including Teams. I will provide some additional resources if folks are interested in how to transition from Model Builder into Python for the first time. The short answer is that if you're used to that, it's if you built models in Model Builder, you can quickly export your model as a Python script. You can open that in Anaconda, and I'll record a small tutorial to help folks with that. And then you can start to manipulate some of those file paths and hit run, and it generally runs really easily. So with that, I will turn it back over to Jason. And again, I want to thank everyone for your patience with some of the technical difficulties today. Inevitably, these things do sometimes happen on these Teams environments. So thank you, everyone, and happy to answer any questions.
Great, thank you, Brian. And yeah, we'll be taking questions from the audience now. If your question does not get asked today, or if you would like to contact our speaker directly, you can find Brian's contact information on a slide that will be presented at the end of today's presentation. And I don't see many questions yet, so I'll allow people to type stuff in for one more minute while I read a little bit more. Please note that an evaluation survey link will be available shortly in the chat box, and this link will also be emailed to you following the webinar if you logged in using your email address. We encourage you to answer the evaluation and give us feedback, as we intend to listen to feedback and improve our webinars wherever we can. If you logged into today's webinar as anonymous, we encourage you to access the evaluation from the chat before the webinar ends. And with that, Brian, you've probably seen a couple of questions in here. I know a number of questions have been answered by both our technical team and our expert modeling team. So I think the first question that didn't get answered was earlier on in your presentation. Someone says that Anaconda won't allow me to create an environment. Can I carry on without it? Would IDLE suffice?
Mo, so that is a very specific and tricky question. My guess is that you might be running into some type of firewall or kind of proxy restriction within your organization that's not allowing Anaconda to write to wherever you are essentially storing the Anaconda files. If you email me, I can try and work with you on that. Anaconda and getting Python and ArcGIS to talk together can sometimes be tricky with corporate and federal firewalls. Let's talk. We can touch base offline. That's a very, very specific in the weed question.
Yeah, and thanks everyone. Another reminder to please do keep typing your questions in as we're going here. Brian, I think you're available to go a few minutes past our scheduled time. Yes, so if folks want to stay on and keep asking questions, we don't have to end in the next 3 minutes. And so I see a few more in here, Brian. The next one is, how do we turn this gridded data into viable input weather data for models like QSWAT?
Yeah, good question. So it depends on, and I'll fully admit I am not a SWAT modeler. I'm a landscape ecologist, and SWAT's tricky. There are packages, though, I know for SWAT and QSWAT that allow for you to take the arrays. So once you've read a raster, whether you use raster.io or various other, you can use GDAL, there's a few other examples. Once they're read in as an array, you can write that to a QSWAT specific file. And I don't know the specific package right off the top of my head, but I will look for that and can put it in the follow-up notes and email.
Okay, next question. Are there any workflows that you are going through that would be limited to working through Anaconda? And they say, my organization uses ArcGIS Pro, which provides a Python executable and allows the install of various other libraries not available in the initial install.
Yeah, so to Anonymous, I use Anaconda, but and we'll provide some information for how to do this for the next one, because what makes Anaconda really powerful is actually the Jupyter notebooks are really nice. I tend to not use Jupyter notebooks when I'm doing more traditional modeling and analysis. I use a Python text editor. I personally like Spider. I've used PyCharms before. There's a few other ones. Notepad, I think Notepad++ is one that a lot of people end up using because it's free and open source. I think where Anaconda really shines, in my opinion, is when you start to link it to ArcPro. And in fact, I think the reason why everyone's being pushed to ArcPro is because of the shift to Python 3 in ArcPro, whereas ArcMap is still stuck in Python 2.7. And so Anaconda can be really, really helpful for that, especially to if you want to start to link up things like machine learning frameworks like Keras and Torch and also be able to do some of the more traditional kind of geospatial prep work in there as well. So those, I do see it as they really can shine together. And then what's nice too, I think in your case, is that in those environments, you have carte blanche. You can put anything and everything you want into them and really kind of tailor a specific environment to your needs for that modeling question or that client or that EPA region that you're working with, et cetera. So yeah, hopefully that helps.
Thanks, Brian. I see that a few questions are getting asked and answered by our support team. Let me just clarify. One question came in. Can you do the same things, presumably that you presented today in R? Is there an advantage with Python to manipulate rasters and vectors? And I see that Kateri, I think, responded to that with a link, but is there anything you'd like to add, Brian?
There is. So Kateri and I are the not dueling, that's not the right word. We are R and Python users. Each has its place and is really useful, but they have a lot of overlap. You can do, I think R is much better for what I would consider to be more kind of traditional analyses, statistical analyses, where Python really shines is when we get into things like the watershed delineation, when we start doing complex geospatial modeling, flow routing, raster manipulation. Those are things that just the Python does faster, is more streamlined, and I think that's where Python kind of is a little bit more efficient in those ways. So I'd love to get to Becky's comment real quick, because I bet a lot of people had that. If you're getting a wget, no module named wget, I am realizing in my haste when we were trying to deal with the technical stuff that we installed the raster stats and the geopandas packages. Some of you may need to install in your environment the wget package. It might be listed as PyWget, PYWGET, or if you type in that search bar for WGET, it should come up. So Becky, I apologize. That's one package that you definitely need for this.
Okay. Next question, Brian. If installing using Conda, which I assume is Anaconda, is wget Python? I don't know. Maybe you can read it. It's totally. A lot of acronyms.
Yep. So for other folks, the question is if you're installing using Conda, which is the I assume that you're using the command line. So there, you can do all of this in a command line, more of kind of a Unix or Linux traditional format as well, which some people really like. It's a little bit, it's just a different way to do it. I believe if you're using Conda or Conda Forge, if you put in PyWget, it should be the one. I believe PyWget writes wget as well, so it should work for you. So.
Okay, and next, Brian, have you tested this using Visual Studio Code?
That's a good question. I haven't personally. I know that that a lot of people use Anaconda in Visual Studio, and so the short answer is I have not. There's lots of resources out there to do that. Anaconda is really trying to kind of be the open source kind of data science platform that they hope everyone uses. They've made it pretty streamlined, so I think it will continue to stay around. It's been around for quite some time and has a lot of support. But I have not. Good luck. Visual Studio is a challenge.
Okay, going back to the Q SWOT question, is there a simple way to get an average value, i.e. Tmax, for a watershed for multiple days from out of PRISM raster data? This average data would act as the weather station for a watershed in a remote area.
Yes. So one of the things that we're going to do in the next webinar is it's largely focused on delineating a watershed. But at the end of that, we are going to also use a package called raster stats or zonal stats, excuse me, to summarize gridded data, and we will actually be using PRISM data for various bound. In this case, we're going to use the watershed that we delineate. That code, the only thing you will have to swap out of it to make it do that for a weather station would be to replace the weather, or replace the PRISM data with the weather station. So it'll be really hopefully apparent how to do that on the next webinar. If you're looking for a before then answer, I would encourage you to look at the raster stats, RASTER STATS package. And I can actually put a link in there as well. It can be cumbersome to install in some of these environments. In fact, it might be beneficial to create an environment with Python 3.7. But raster stats is essentially zonal stats. It's a package that allows you to summarize geospatial raster data sets based on vector geometries. And it's very fast and very good, so I highly recommend it. And I just put the Python hosted file or landing page, excuse me, in the chat.
Okay, thanks, Brian. Another question that's maybe a little more detailed and kind of error checking. The final line of the Jupyter Notebook won't run has the following name errors. Is there a reason why? That might require a bit of a nuanced answer, I'm guessing.
So the real helpful line in there is name error. Basically, name show is not defined. So if we, and I apologize, I didn't realize I was still sharing my screen. It could be that somewhere up here, you may not have loaded. See if it works for me. Sorry, run that. My guess is that we need to add you may need to add a line that says, I'll just type it here for right now. Raster.io import show. I think that's it off the top of my head. I will look into that one. That is a specific one that we'll definitely need to know. I'll get back to that one.
Okay.
Anonymous,
Thanks.
bear with me. I'm going to find an answer for you.
Next question. Will there be a multi-processing workflow dealing with large data sets?
Yes. So I think today we have a really, with 200, 300 people, we have a really wide, what we've found historically is we have a really wide range of users, ranging from folks who obviously are, looking at coding in QSWAT and things like that, or, Visual Basic, for example, down to kind of the other end of the spectrum where folks are maybe not necessarily opening ArcMap for the first time, but certainly maybe looking at Python code at a relatively newer level. So today was really focused on kind of trying to lay some of the groundwork, file path structures, how we download data from FTPs, how we get that data from a zip file into a geospatial format, how we clip that data. The next webinar, since this is kind of a two-part webinar, will really be focused on how do we delineate a watershed. That's a multi-stage process, so that's going to include things like taking your DEM, delineating it, filling the sinks, doing flow routing, and then how do we summarize various gridded data sets, PRISM climate, for example, to that watershed boundary. If we have time, we may even throw in some national land cover data and how we summarize that as well. So there will be there. It's a step-by-step process is what I would say.
Thanks, Brian. I think we're kind of getting to the end of the questions. If you'd like to advance to the next slide, I believe. And yep. So Brian and Kateri have put their contact information on here and are willing to answer some questions related to the presentation they had today. Regarding the water quality modeling work group, you'll see our link there with links to all of our previous webinars and some other information about our work group. And again, if you have any questions that have not been answered, please feel free to reach out directly to our speaker. As you see the contact on the slide. And I think you can go to the next topic. Next slide. Yeah. You can find information on future webinars as well as a recording of today's presentation on our water modeling workgroup website. The link to that page is shown on the bottom of the slide. You can see the next topic is, as Brian has referenced many times, is watershed delineation in ArcGIS and Python. And we don't have a firm date set for that, but we'll get that out to folks soon via the usual ways that you hear about this through the EPA listserv and website. As a reminder, you can find a link to an evaluation in the chat pod, and I think Corey, I'm hoping that's up. I can't see yet, but we encourage you to answer the evaluation and give us feedback to help us continue making improvements to this webinar series. And next slide. Additionally, if you'd like to receive updates on the webinars, please sign up on the EPA website on the quote, About the Office of Water website page, and that link is on your screen. What you'll do there is navigate to the Subscribe to EPA's Water News link found in the green Related Information box on the bottom right side. Select the modeling webinar email list for these webinars and feel free to add any other topics of interest. And again, that's all at that link you see on the page here. I'm guessing many of you heard about today's webinar via that list that's available to sign up at that website. And as a reminder, you'll be sent an email with the certificate of attendance for today. If you've logged into this webinar as anonymous and would like to receive credit for the certificate, or you would like to receive the certificate, excuse me, please email our technical support team. The technical support email address is in your registration confirmation email. At this time, I'd like to conclude today's webinar. Thank you to Brian and Kateri, our amazing speakers for this webinar series. And of course, thanks for everyone who joined us. That ends the webinar for today, and we will see you next time.